section, and then same for the next half, the operations operations, which is a bit longer, and some advanced topics, which I hope to also give you time to do some exercises this morning. So anyway, I'm going to go ahead and get started. Welcome to the all morning Pandas introduction course as part of the Python for HPC course. So hopefully some of you have used Pandas before, so for some of you this will be a complete introduction, and for others, hopefully you'll learn something new about some of the more advanced topics that we'll be covering a little bit later. So Pandas is short for Panel Data Analysis, and it was originally developed as a data library, as a function library for cleaning, organizing, and statistically analyzing moderately large data sets. That's up to about 3 gigabytes. If you get bigger than 3 gigabytes, you'll typically need to have bring in a second package like Dask or Polars to add additional functionality. But for most data sets, Pandas is fine. So you get lots and lots of features. You get automatic and explicit data alignment, so you can extract cells or rows or columns by name instead of having to fiddle with indices. You can import and export a wide variety of data formats, including Excel files, JSON, HDF5, SQLite files, or SQLite databases. The data structures support a wide variety of data types in any combination, more or less. And there's hundreds of functions for performing all sorts of cleaning and reshaping and analysis functions. What is that noise? Needed a little percussive maintenance. There's also a relatively simple interface with a package that we'll be talking about later, which is the Seaborn plotting library. And increasingly, also, you can just interface straightforwardly with Matplotlib. And you can get easy multi-threading with a Numba engine. And I'll show that towards the end of this session. So I already mentioned the limits for data size. Pandas is also designed for 2-dimensional data structures. So basically arrays of rows and columns of data values. If you have something like image data or image cubes, you probably want to use a different package called Xarray, which expands similar Pandas functions to higher dimensional data structures. So hopefully everybody's already got the exercises because of the tarball. And so let's talk about loading and running. For most of these, the commands that you need to run are right here at the top that you can just copy straight up. So at HPC2N and most of the other places, or most of the other facilities that are featured here, you'll need to load a GCC package, a Python package, and a SciPy bundle. So that's true at HPC2N. That's true at LUNARC. At UPPMAX, everything you need is included in this Python 3.11.8 on the Rackham machine. On Tetralith, you have to load the usual stuff plus this build tools easy build module. And on Dardel, the Cray Python packages include NumPy, SciPy, and Pandas, and don't require any prerequisites. But if you need to do any visualization, like with Matplotlib, You'll need to load that separately, and you can see in others of these, we also have matplotlib loaded. And this TK enter here is so that you can run the matplotlib functions from the command line and have it still pop out a GUI. If you were at the matplotlib session last week, you more or less know what this TK enter is doing for you. And but if you're on Dardel and using SSH with X forwarding, you need the PDC 23.12 and then matplotlib 3.82 dash all of this gobbledygook, and that will allow you to plot some of the data and visualize it as a curve. Anyway, so hopefully everyone has that loaded. If you need, so Pandas specifically is part of this SciPy bundle, unless you're using an Anaconda distribution for Python. So if you're using the pip packages, in other words, SciPy bundles are the ones that contain Pandas, and that requires Python 3.8 or newer. Did I see a hand go up? No. Okay. All right. So let's talk about when you should use Python or Pandas. Well, more or less, we already covered this table. If your data is 1D or 2D, Pandas is usually good, unless it's greater than 3 gigabytes in memory, and then you might have to add Dask or polars to process it. And if it's in an n-dimensional array where n is greater than 2, you might need xarray. And we've already covered the features list that I described at the very beginning is essentially covers most of these learning objectives. You're going to learn the input and output, how to inspect, clean, and sort data for later operations, how to do some of the basic and vectorized operations. You'll learn about what are group by objects and how they're used, and how to compare data, implement complex or user-defined functions, and perform windowed operations, or at least this is what's covered on this website. So a few of these we may have to skip in the interest, we may have to gloss over in the interest of time. And for advanced topics, we'll talk, if we have time, and I don't think we will, we'll cover a little bit about time series. We will cover memory saving data types because I know this is of interest to everyone with HPC, for HPC usage, and we'll touch on a little bit about how to prepare for machine learning and AI. I see a hand up, Linus?
Yes, quickly. If our data is both multidimensional and large, which generally goes together, do we need both xarray and Dask, or does xarray take care of the largeness of the data?
I think xarray takes care of the largeness, but I'm not sure. I haven't used it much. I mainly use Pandas because it's enough for my data sets. Sorry, I couldn't be of more help. Okay. After the Pandas sessions, we'll have a short session on plotting with Seaborn, which is a package that makes it very easy to create publication-ready statistical plots from Pandas data frames. So, since I mentioned data frames, now let's go on to the basic data types and object classes. The main two that you will see are series and data frames. Series are one-dimensional, data frames are two-dimensional. So for series, the indices or labels attached to every entry are customizable and that makes each cell accessible by name. For data frames, you get that feature and the same feature along the column axis. In a Pandas data frame, every column is a series. And all entries are accessible by column and row labels or indices. Any function that works with a data frame will work with a series unless the function specifically requires column arguments. And you can reassign the column labels and row labels or indices as needed. So for the rest of this lesson, if I'm using a data frame in a sample function, it'll be abbreviated as DF. And if series appear, they'll be abbreviated as SER or SER. There are literally hundreds of methods and attributes for both series and data frames. These 5 right here are the most important to remember, but the documentation for Pandas is extremely extensive. So if you want to get started with this, I recommend you start with the 10 minutes to Pandas. That'll give you, that's what this lecture is based on. It's mostly this 10 minutes to Pandas section, which is not 10 minutes. You need a lot more than that to get through this, but you can easily find the most important attributes and what they output in the official documents. But I've pulled out the most important ones here. So if you call .index off of a data frame, it returns a list of row labels. And similarly, columns returns a list of the column labels. Both of these are data type index. And you can get the data types by column by calling df.dtypes. df.shape gives a tuple of the number of rows and columns. And df.values returns the data frame converted to a NumPy array, which scraps the that typically scraps the column names and indices, but you can set it to include the row indices as a column. This is also applicable to df.columns and df.index. If you call .values off of those, you get a NumPy array for the lists of columns or rows. And so the other important thing to know is that Pandas assigns the data in a series or data frame by column based on either built-in or NumPy data types or other formatting cues. And the data types that you'll see are typically one of the following. You'll get, if it's pure numerical data, it'll be either float 64 or int 64 unless you convert to something else. The object data type stores any of the string, Boolean, list, tuple, or mixed data types. A lot of times, if you are expecting a numerical column and you see it classed as typed object, that means that there's something malformed in the data that you need to clean. There's also Pandas also has many functions and attributes devoted to time series. So you'll see occasionally see date time, time delta, or period data types if you have time series data. The first couple are based on NumPy data types of the same name. And period is a time interval data type specified by a start date time and recurrence rate. We won't really have time to cover the time series in depth, but you'll have a little exercise that very briefly introduces you to those in your exercise set. There are also a few specialized data types that are important for saving memory or performing windowed operations. So there's a categorical type which stores non-numeric data with very few unique values, and the unique values are stored in the attribute categories, which are mapped to a very low bit size integer, and those integers replace the actual values of the data frame at where it's stored in memory. And that can save a lot of memory usage, which I'll demonstrate very shortly. There's also an interval data type for Pandas discretizing functions, where you're binning things into, where you're like converting numerical data types into like bins or or like range brackets. And there's a sparse data type for SciPy sparse matrices. This is all far from an exhaustive list, but it's all we really have time to touch on today. Skip the note on indices. You can look at that later. It doesn't really matter for the examples that we'll be using. I have to mention briefly that Pandas documentation is a little bit inconsistent for how for the naming conventions of row and column labels or indices, depending on context. Most of the time when I'm saying indices, I'm referring to just row labels when they're numerical, but sometimes it might refer to both row and column labels if those are numeric. But I might also use indices to refer to row labels, even if those row labels are not numeric. Columns usually refers to just the, columns may refer to the labels or contents of the columns collectively, or only the labels. And if you use SQL-like functions, the column labels and sometimes also the row indices will be called keys. We won't cover those very much today, but you will see that if you have to work with SQL data, SQL type data and functions that perform SQL-like functionality. A column label might also be called a name in the optional, particularly as the optional series label. And the reason you might label a series is if you want to add it to a data frame later. All right, let's talk about input and output. There are a ton of data types that Pandas can read in and write to. This table is not even complete, but the three that I've highlighted in bold are the ones that you'll use by far the most often. So if you have a plain text file, even though it says read CSV as if it's only for comma separated values files, this is also the function that you use for ASCII tables that are that use a standard delimiter like a tab or a certain number of spaces. And you just have to change the separator to something other than a comma for other ASCII text files. It also works on Microsoft Excel files and open document files. So if you have these types of tables, you can very easily read them in without any extra steps. And you can even pick out individual sheets and write to individual sheets. So read Excel is the one for read Excel opens both Excel files and open document formats. It's just that if you're using open document format, you'll need this engine equals ODF quar. I'm leaving it as an exercise to the reader to determine what quargs are needed for whatever data type that you choose to read in. The documentation on these is very extensive. So like here's this IO tools page. Here's a table that you can then click and go to read CSV. And if I pull up the actual page for it, you can see this big long list of all the quarks that you can do, or you can use. So it even has things like chunk size if you need to read in very large data tables by chunks. Anyway, so as a very quick example, if you have this this exoplanets data file from the MATLAB exercises, you can also read that in with as a data frame. And I will go ahead and pull up a Jupyter Lab page. Give it say 6 hours just to be absolutely safe. And I'll push this in the back in a second. So, keeps opening untitled. So I'm going to open this. I've got a few examples. So let's start by importing pandas and NumPy. And here I've just initialized a very basic data frame with a NumPy array that I've reshaped 4x3, and I've given it some column labels. I've given it this, and I've given it these 3 column labels. And then if I print it, you'll see that it's been automatically assigned numerical indices. I'll go over the this is a little bit out of order. I meant I will cover manually creating data frames in a second, but this is the command that you need to input to open a data frame. And I have this index call equals 0. What that means is that instead of arbitrarily assigning all the rows different numerical indices, then it takes the first column as the indices. And if I print the first few rows, you'll see what that looks like. So I'm going to print what's called the head. This little head function prints by default, it prints the first 5 rows. You can also enter a different number to print more or fewer than that. And there's also a tail function that does the same thing, except it pulls from the end of the data frame instead of the beginning. But anyway, this is what this data table looks like if I print it out. And you can see that instead of having 0, 1, 2, and 3 for the or 0, 1, and 2 for the indices, the index column is called name, and it has all these fancy exoplanet names as the index. So now, all right, so I've shown you how to import the data. So now let's, if I output it, it's I could write out to a different folder, and if I wanted to give it for some reason the pipe operator as a separator and convert the decimals to a European style with a comma instead of a period, I can do that. That the toCSV function covers that. And most reader functions include this index call equals 0, which lets you set the first column as the row labels. I am not doing good on time. Building a data frame from scratch can also be fairly easy if you're using like NumPy arrays or lists, 2D lists and arrays. Those can be converted directly to series and data frames. You can also get them from record arrays or from dictionaries. Those functions are available as well. And I went over an example about how you can do that in how you can do that in the demo. So as I wrote here, I've given a NumPy data array. I've given an array that's 4 by 3, and I've passed that to the pandas.dataframe function. I've assigned it to these columns. Let's give it also some indices. So I'm going to set index equals, let me start this at, I'm going to do like W, X, Y, Z. And now the index columns are W, X, Y, and Z instead of 0, 1, 2, 3. You can also use this to change the starting index. That's easy enough. And you can also convert data frames back to NumPy or to dictionary, to records, or to string. So let's talk about the inspection, cleaning, and sorting and merging functions. So I already showed you an example with head and tail. This .info function prints the number of rows with their first and last index values. The titles, the index numbers, the counts of the number of valid data entries, data types of the columns, and the estimated size of DF in memory. But you don't want to rely on this memory estimate because it's only accurate for numerical columns. Here, I'm not going to cover all of these different attributes because we're running a little bit behind, but I will talk a little bit more about this memory usage function. So by default, if you use df.memory usage, that it returns the estimated memory usage of each column but only at the location where the main data frame is stored. And so that means the sum of the estimated memory size of all the columns is the same as what is included in df.info, which is not exactly accurate. If you set deep equals true, the sizes of strings and other non-numeric data are factored in, which gives a much better size of the better estimate of the total size in memory. And the reason that this is that the data frame sort of has a fixed width at the main location in memory, but for strings and other non-numeric data, what's stored at that location is a pointer to wherever these non-fixed width values can fit in memory, which is in a different location. So so it's only the numeric data that's being kept in a contiguous location. So for the example of the data frame that the exoplanets data frame that you worked with for the if you attended the Matplotlib session and that we loaded earlier, this is what you get if you print the the df.info. So you can see the indices, the data columns, the column names, the counts of non-null entries, data type. You'll see that mass and radius are object type here, and that's because we need to do some repairs. But anyway, if I print the memory usage with as the default, then all of the index or all of the columns and the index sizes are take up this many bytes. Whereas if I set deep equals true, now the index column has expanded by a factor of almost 10, well, almost an order of magnitude. And the same for the planet type column, the detection method column, and because these have a mistake in them, the mass and radius columns. So we'll treat those in a few minutes. So on to data selection and syntax. If you can only remember two commands, remember the .lock and .ilock. That's where my brain was flaking earlier. So if you want to select a column, it's just basic dictionary-like syntax. So you can call it df and then square brackets in the name of the column. Or you can call it df dot in the name of the column as long as the column name as long as the column name doesn't contain any spaces, then you can use this dot syntax. But if you want to get, for example, get one row by index, or if you want to get one row by index, then you use .ilock, and .ilock will return the name of the row. So let's try this again. Did I print out any of these? Yes. So let me try this again. df.ilock 55 Cambry E. Oh, sorry, excess. I titled it excess. This is new. I swear this is new. So let's do. Oops, that was supposed to be a colon. There. So .lock gives you, .lock is what you use if you want to index by row names and column names. And you can give it a list or a single entry to get to if you want to get like an individual cell, you might do let's see, type that tells you that's a super Earth planet because that's a single cell, but you can also get multiple cells. So I could do something like planet type, and let's get the actual mass. So now you can see lock allows you to extract one or more cells by name. And you can input either a single index or name, or a list of the rows or columns that you want to get. And there's also this ilock, and that lets you get rows and columns by number. But for ilock, the indices have to be numeric. So if you can only remember two cells, you can only remember a few of these cells, just remember .lock and .ilock. There's also these .at and .iat functions. I don't bother remembering them because they're kind of redundant, except they extract a single cell and remove the data frame wrapping, so to speak. You can also use conditional selection with these operators and with binary comparison operators and most logical operators inside of these square brackets with some restrictions. So you can use bitwise logical operators with like the ampersand and the pipe and the caret and the tilde. Those have to be used instead of these plain English versions, and, or, XOR, and not, unless the conditions are passed as a string to this df.query function, which we're not going to go into, but it's available on the documentation. So also, when 2 or more conditions are specified, each individual's condition must be bracketed by parentheses, or else the code will raise a type error. This is an example here. So it's the same data frame that I showed you in the demo, and I'm pulling out the locations of planets where the index string contains PSR. That means it's orbiting a type of dead star called a pulsar. And I'm joining that with the requirement that the discovery date is before the year 2000. And then and then I'm just pulling out the planet type column because this is .lock, and I wanted to keep this output short. And that's what this output looks like here. Also, the is operator does not work within .lock. You'll need to use .isin or .not in or .string contains to check for the presence of substrings, or the presence of other data points that are specific to your data set. All right, let's talk about handling bad and missing data. There are a couple of special functions that Pandas has created for detecting NANs, called .isInA and .notInA. And the reason for that is that Pandas has Pandas also allows a date-time equivalent of NAN called not a time, or NAT. And these .isInA and .notInA functions will also work on that type of value. And you have the option of removing entire rows or columns containing invalid data, or filling invalid data with a fixed value. You can interpolate, although the use cases for this can be quite restricted. You can drop duplicates. If you find that there are entire columns of valid data that you nevertheless do not need, you can just use this df.drop and specify an axis. A lot of these have this axis quad where you say, where you can either write axis equals 0 or quotes index, or you can write axis equals 1 or in quotes columns to drop, to choose whether to drop rows or columns. You can also mask values without getting rid of them. And you can even use this mask function to replace them with other values. And of course, there's this df.replace, which is similar to the string replace function, but much more expansive. It lets you handle numbers as well, and also other data types. It's very flexible, but you'll have to see the documents because the list of quarks and arguments is very, very extensive. There are a couple of restrictions though. Pandas does not natively detect infinities. You'll have to convert to NumPy and check and use isinf to check for those. And it also white spaces as fill values are assumed to be, Pandas assumes that white spaces are intentional, even if they're in numeric columns, because, as I said at the very beginning, this was originally developed for financial information. So numerical columns might be things like zip codes, which in Sweden have a space between the first, I think it's either the first 2 and last 3 or the first 3 and the last 2. But anyway, Pandas assumes white spaces in numbers are intentional, so .is in A will not detect if you have a white space that's being used as a fill value. In fact, if you use a white space as a fill value in a numeric column, the entire numeric column will be converted to an object type, and it will take up much more space in memory. So one of the in the exoplanets database that I showed you before, the mass column and the radius column, I already know off the top of my head because I've worked with this so much. That has white spaces as fill values, as invalid value markers for the mass and radius columns. So it was necessary to replace the mass and radius in the mass and radius columns. It was necessary to call the replace function off of that to replace these white spaces with nans and then convert the whole columns to float. And I also masked the eccentricity column because a lot of the eccentricity column had a value of 0, which is kind of a dumb. That's an assumed value. It's not a. It's not like it's not like the vast majority of planets have identically circular orbits. They're not. So anyway, once I've made that conversion, now these mass and radius columns, if I print out the info again, they are now float 64, and the memory usage has dropped a little bit. All right, so now let's talk about sorting and merging. For some operations, including all merging operations and you have to sort the data frames first. So there are a couple of sorting functions. You can sort by values, or you can sort the indices. The sort index function rearranges the rows or columns so that the indices or the column labels are in alphanumeric order. Important to note that all uppercase letters are sorted ahead of all lowercase letters. So a row named capital Z zebra would be placed before a row named lowercase a aardvark. But you can use this key quad to tell sort or ignore capitalization by, for instance, passing this string.lower function. And there's a sort values function, and that sorts the series or data frames by the values of whichever rows or columns you pass to this by quad. If you have to join 2 or more data frames together, there are lots of different ways to do that, as long as you sorted them first. If you just want to extend a data frame by rows, you can just, particularly along a shared row or column index, you can use this concat function, which looks a lot like the NumPy version. But for most other functions, or for most other purposes, you'll need to use something like this merge function, which has a few different variants, like this merge ordered, merged as of, and join, which is merge under the hood. Those use SQL style set operations to combine the data. And the visual of it is this right here. So inner join is like taking an intersection. A full outer join takes basically all of the data that's in both data frames and figures out how to it creates new columns and pads them as needed, right? And it creates new rows and pads them as needed for the wherever one of the other data frame is missing rows or columns. There's also left outer join and right outer join, and that's kind of what it shows. It includes all of the values of the left array, including what's what is shared with the, and includes all the values of the left data frame plus any that are, that the right data frame shares, and the same, and the obverse for right join. There's also these combine functions. The one I use between these two combined functions, I only really use combine first, and that's really handy because you can use a second data frame to fill missing values in your first data frame wherever they share indices. So you can sort of use a second data frame to inject missing values into your primary data frame. So, and that's really handy. I'm not going to go into these examples because they get very, very, very complicated very quickly, and we're running low on time. So just to get us back up to speed, we'll touch on group by objects, and then we'll go to the break. One of the most powerful Pandas tools is this group by method. And that lets you organize data hierarchically and run statistical analysis on different groups of the data simultaneously. And that lets you sort the data. According to the values of one or more columns, if they're like non-numeric, for instance. But you can also use as I'll show later, you can use discretizing functions to create groups out of numerical data by sort of like binning them, and you can then assign those bins names. But I digress. The basic syntax for grouping is df.groupby, and if you only use a single column, you can use just by equals and then the name of the column. If you have multiple columns that you're grouping by, you can use you can pass those as a list. You can also group by rows, but you have to take the transpose of the data frame. For the main utility of these group by functions is that if you call aggregate methods, or like most statistical functions, so like the median, the mean, the mode, the standard deviation, those will be evaluated for every single group individually. And you can also retrieve the nth row of any given group. And you can even assign n to be a negative number to get the to index backwards from the end. You can also select groups in group by objects by category name with this .get group .cat. Note that even if you only are selecting one of them, it still has to be in parentheses and then the name of whatever column you're getting, and then a comma, and then a closing parentheses. I don't know why they decided to go this way, but this is not a bug. They actually originally allowed you to give it an isolated string without the parentheses and the comma, and then they decided that was not allowed anymore. Anyway, and if you have a group by object, you can call .groups to iterate over it. To iterate over the groups. And separate functions, as we'll talk about a little bit later when we get to the operation sections, we'll talk about how you can broadcast to each group separately, separate functions in one command. So let's look at the recurring example. So there's in this exoplanets data frame, there are 5 planet types. So you have the gas giant, super Earth, Neptune-like, and terrestrial. And then you have this little unknown column that has like a handful in there. And if I do a group by, and then I print the first row of every group, this is the output. And it's split over several lines because it's too wide. But this is all the same. Each one of these is the same row if it has the same name. All right. With we have 5 minutes left, so we'll before we go to the break. So now I'll start taking questions. Everybody a couple of minutes to think. And we will pick up right where we left off, which is we left off at the end of group by group by operations. So now we'll talk about, or we left off on group by objects, so now we will start with operations. So let's talk about all the fancy things you can do with a, no, I don't want to do that, go away. All the fancy things that you can do with Pandas data structures. You can iterate over data frames, series, and group by objects if you need to, if you absolutely need to, but it's very slow and you should avoid doing that whenever possible. Fortunately, most math functions, statistical functions, string methods, functions, most of those types of operations, at least in the basic sense, are vectorized. They can operate on entire rows, columns, groups, or the whole data frame at once, simultaneously. So now I'll be teaching you a little bit about how to avoid having to iterate down rows and down columns slowly. Start with strings. You already saw something that was a little bit similar to a string method, which was the replace function. There's a string.replace, and then there's a regular replace. And I would recommend the regular replace for if you have to replace like a invalid value with a number, or and change the data type, like I showed before with the sanitation operation. But there is a string equivalent, and in fact, most of the built-in string methods in Python can be applied to Pandas structures using this .string accessor, and then following that with the dot and then the name of the method in parentheses. So you have the standard upper and lower. You have the R strip. You have the R split, and with or without R, or the strip with or without R. And of course, I mentioned the replace. There are also statistics functions. Pretty much all the statistic functions that you might be familiar with from NumPy, and a few of the SciPy mstats functions. All of those can be called as aggregate methods on data frames, series, any subset thereof, or group by objects. And all of them ignore NANS by default, so you don't have to do any sort of masking or dropping in order to use these. Just one caveat: for data frames and group by objects that have more than one column, you have to set numeric only equals true as a quark of these methods in order to exclude non-numeric data. And you also have to specify whether to aggregate along rows or columns. Although these methods, because if you don't set numeric only equals true, then it will try to, for instance, take the absolute value, like if you're using the absolute value function, for instance. Sorry, not absolute value. That's a bad example. Use, for instance, if you're using median, and then if you forget to set numeric only equals true, it might try to set the median of a, like in the exoplanets data frame, it might try to take the median of the detection method, and those are all strings, so that doesn't make any sense. So it's going to raise an error. Also, if you were to call like the mean function or the standard deviation function, by default, you're going to aggregate over the entire data frame and not just the rows and columns that make sense to do, where that would make sense. So you would need to specify an axis like axis equals axis equals 1 to aggregate down columns. So these are the list of NumPy-like methods that are available. Pandas adds a cumulative maximum and cumulative minimum function as well. And SciPy, for SciPy-like methods, you get skew, kurtosis, and correlation, and I think that's standard error of the mean. So here's an example using the group by object that we looked at before. So I've got the I've downloaded a fixed version of the exoplanets data file that has all the fixes to the mass and radius column already implemented. I grouped it again by planet type, and now I'm taking the median mass of those groups. So what that returns is that the typical terrestrial planet mass is a little bit less than Earth mass. Super Earths are average around, have a median of like 3 Earth masses. Neptune-like planets have a median of 8 Earth masses, and then gas giants are actually a little bit more the median of those is a little bit more massive than Jupiter. So let me see, do I have the demo here? I can do another version. So let's do that, and let's see, did it implement the change? No, the change was not implemented here. So let's implement that. Okay, that's different. Let's fix that. And now this will work. So there we go. So now I've taken the mean instead in this example. So you can see that bumps up all these values a little bit. Anyway, so this is something you can try yourself with the data frames that are supplied as examples. Now, binary operations. The normal math operators that you're used to, like that are in this column here, those all work just the same as usual, as long as the both data structures that you're using are either the same shape, or if one of them is a scalar. So you can add the same value to every cell of a data frame, or or every cell of a series, and the plus sign works just fine. Or you could add 2 data frames of identical shape, and then the plus operator would be fine. However, things change a bit if you're trying to operate on 2 differently shaped data structures. Like, for instance, if one of them is a series and one of them is a data frame, then you need one of these data frame methods. And these I've shown with the equivalent scalar operator next to them. So you have add, subtract, multiply, divide, power, and modulus. And most of these have have a reverse option that you can include by adding an R before the name of the method. For instance, if you're dividing one data frame by another of a slightly different shape, like df1.div df2 is equivalent to dividing df1 by df2, and then df1.rdiv df2 is equivalent to taking the reciprocal. Comparative methods are sort of similar to the other binary operators, in that they work if you're comparing a series or data frame to a single value scalar. But if you want to compare any two Pandas data structures element-wise, you need a special comparison method. And then you can also add any .any or .all to aggregate along along the column axis, or if you want to Boolean compress the entire output, you can add it. You can invoke these twice. If any of you have used Fortran, the names of these Pandas methods might look a little familiar. That's just a tip that helps me remember what these operators are. So for the greater than, you have a .gt, less than LT, and so on. And you can, if you want to find discrepant values between two data frames, as long as any two data frames are identically indexed, so that means identical row and column labels in the same order, and that's important. So you have to sort them. But once you've done that, then you can call compare off of the first data frame and input a second data frame, and that can be used to quickly define discrepancies. However, that method does not find if there are two values that look the same but are different data types. For that, you can use this pandas.testing.assert frame equal, or pandas.testing.assert series equal. And if you see an assertion error, then that means even though the data look identical, somewhere in there is a data type that's different. So you might have, where you might be comparing series and data frames that are otherwise identical, but one is integer and one is float, and just looks like integers. So like 1 versus 1.0, that kind of thing. And there's an example in your in your examples, there is a part where you will be comparing two data tables, and they each have a set of the region names of different administrative districts of Italy, and a couple of those names have, like, in one data set it has a hyphen, in another set it's got a space, and that's something that you can use the compare to find. And that's useful if you want to make sure that you're able to cross-link two tables for pulling values from one to the other. And that's handy if you have these if you have a more complex or user-defined function where you need to, for instance, take values from one data frame and apply them and manipulate them and then apply them to another data frame. So there are 4 main methods if you have a more complex or user-defined function to apply. If you want to apply this function element by element, then what you want is map. That takes a scalar function and broadcasts it to every element of the data structure. And what I mean by scalar function is that it takes one value and outputs another value. It does not take data frames, does not take arrays as input or output. Most of the time with map, it's just easier to apply vectorized functions, even if you have to chain them. For instance, multiplying a data frame by the power of 0.5 is faster than applying the square root function with map. But you could do it that way. And map also does not accept group by objects. So this example here, this is something you might see in, this is meant to look kind of vaguely like chemistry rate equations. And so this is So this is a complicated function that's designed to take different values and output and run them through different functions based on the value. This is a prime use case for map where you need the function that's being applied to vary with the value. Then you have ag and transform, which are sort of complementary to each other. Ag applies a reducing function like the mean or median. These are functions that aggregate down rows or columns or over the entire data frame. And unlike the more generalized apply function, ag preserves groups in the output. So if you're applying multiple aggregating functions at the same time, like I've done here in this example, you can. So in this case, what I'm doing is I'm using ag to essentially apply and format two aggregating functions at the same time, and output them as strings, properly formatted. And then I'm applying it to this group by object where I've grouped by both detection method and planet type, and then now you can see in the output, it's grouped by the detection method here, and then each represented group within these detection method bins is here in the second column, and then finally the actual output of the functions is over here in this right column. So it even sorts the output for when you print this stuff, it even prints it out nicely formatted for you. So that's nice. And transform is sort of the obverse of ag, where you take you call a function and it broadcasts to every cell in the data frame. And you can even have expanding functions that turn a single cell's output into an entire row or entire column. Ooh, what happened there? It looks like that missed a timeout. That's supposed to be X times Y, not that. Anyway, so you can pass multiple functions at the same time as a list of function names or a dictionary of row and column names where the row and column names are keys, and then the functions to apply to each are passed as values. And you can pass lambda functions in a dictionary, but not a list. So it's important, but it is important to note that if you transform a data frame with an X number of columns by a list of Y functions, that yields something called a hierarchical data frame. And that yields X times Y columns, where and then you have the column names are arranged in two tiers, where you have the original column names at the top level, and then the names of the functions that you pass as the second level. And then the values are split over those. You can see in the structure down here at the bottom, the columns are split by the functions. And it's important to know that you also do not want to allow transform to modify your data structure in place. You need to return the value as a copy. See a question in the. Okay, hands-on coding. This is this would be a bit difficult for. It'd be a bit difficult for hands-on coding in this particular section, but in if we get to in the advanced topics, we'll cover a couple of things that you can code along with. So let's go to. So one last thing on the user-defined and complex functions. For apply, this is sort of the if all else fails function. This can handle aggregating, broadcasting, and expanding functions, but it's a lot slower. However, it might still be a bit more intuitive if your function varies by group, because transform receives group by objects in two parts. So the original columns split into series, and then the groups themselves as data frames. And that's hard to work with if you're not using a predefined function. I'm going to kind of gloss over windowing operations because we're short on time, but the main thing to remember is that you can use these rolling or expanding or exponentially weighted moving windows to apply all of the previously mentioned operations over windows. Oh, something disappeared here. Okay, let's do I have something here? Built-in plotting methods. No, that's not it. Okay. So, if you want to do a code along demonstration, so let's try one with ag. That's a simple one. So I've initialized a does anyone need help loading a example data, the example data frame? If you have the fixed version, I would recommend going ahead and loading that one. Let's see. Don't see any hands up. So I want you to start by, once you've loaded it into a data frame called exos. Oh, yes, Alfredo?
Sorry, can you just increase a little bit the size of the font, if it's possible?
Is that good?
Thank you so much. Thanks so much.
Yeah, okay. So, if we've got so we've got these exoplanets and you want to group them by planet type. You can see the gas giant, Neptune-like, super Earth, and terrestrial. Then you could, let's say, let's just change this up and call the radius, and change that to Earth units, and change this back to median, because this is a nice one. All right. So was everyone able to do this in their own little Jupyter notebooks? Everyone who wants to code along. All right, so now what we're going to do is we're going to try ag. And for this one, I want you to call, yes, I see a raised hand. Maria?
Hi there. So I have a question that might be way past, but I was wondering, is it possible to be able to see all the active data frames, whatever we have called, as a list of, oh yeah, this is what you have defined so far, instead of having it as a, in your code?
So not in Jupyter, but if you have, I usually use spiders. So
Okay, so it is a matter of the type of interface we're using rather than.
Yeah.
Okay.
Yeah, so the interface that you're using sort of determines whether or not you can view all the variables. However, if you want to explore what your what any given variable looks like, for instance, this group by object, I've already assigned this. So let's say group pt dot head. Come on, there. Then that will print the first five rows of each of these types, except for this unknown column, which only has 3.
Okay. So it is a matter of what we're using, and with Jupyter, we just need to remember what we have.
Yeah.
Okay, thank you.
You're welcome. Okay. So for a little quick exercise, I have this little thing that you can try. And what this will do is, this little dictionary here, what you're doing is you're applying the mean function, the NumPy mean function, to the mass column, the median function to the radius column, and the quantile function to the orbital period column. The quantile is like the default output is the 50th percentile. So as you can see, these are all very, very short. The known exoplanets are biased towards, the detection methods tend to be biased towards a very short period, very close to exoplanets. So that's why you get this result. Is everyone able to, I'm going to change this to orbital radius in AU. AU, by the way, is the distance between the Earth and the Sun on average. So this is what you should get as an output if you use the same input that I did. All right, is everyone, raise your hand if you're still working? Okay. Let's just talk very briefly about the speed up with the Numba engine. If I can just center this right. If you have Numba installed or able to import it, then a lot of these functions can be sped up by using the engine equals Numba and setting engine quarks and then putting in the dictionary brackets parallel : true. Just so you know, though, parallelization occurs column-wise, so performance will only be boosted if the function is repeated many times over many columns. So this is an example here where I'm doing a sort of nonsense operation just to show as a demonstration on the exoplanets data frame, where I'm taking like a rolling mean over like I'm resampling the array to like 250,000 times to an array called stuff, and then I'm taking a rolling mean over it, and then I'm trying once with engine equals Numba. This is 5 columns, by the way. Engine equals Numba, and then engine quarks parallel equals true, and you get a speed up of a factor of about 3 here. So we're running very low on time, and you can check your work with the dot plot wrapper if you want to look at some of what you're outputting. So this is an example with the data frame, with the example data frame again, and let's. For the advanced topics, I would say the most important one that we need to look at before I let you go is the efficient data types section. So in the interest of time, this is the last section we'll be covering. So then let's go. We're already a little over time, but I think you guys need to know about this categorical data type, because this is really, really handy for reducing data usage. So if you have a column that's non-numeric and has very few unique values, then you can save a lot of data by, or you can save a lot of memory by storing it as categorical data type, by adding You can set the column equal to the name of the column with the .as type category. And so let me show you what that does to the memory usage. Oh, why is it not in here? Ah, there it is. Okay, so what I've done is I've pulled out just the planet type column, which as you might remember has 5 unique data types, and there's 5,200 or 5,250 rows total. So if I convert just that column to categorical data type, it cuts the memory usage in half. I believe I have an example in here where I've converted both the planet type and the detection method columns to categorical. So let's first print the before value. So you can see the indices also occupy quite a bit of memory, but you're not going to save any memory by turning those into categorical because there's so many unique values. They're all, well, by definition, they're all unique. But the planet type column and the detection method columns, as you can see, use almost 10 times as much memory as the float type columns. However, if I convert these two to type category, then what it's doing is that it's matching each value to a very small integer bit value that it saves in the location of the array in contiguous memory, and then it only has to store 1 copy of the unique values at a different location. So now if I do the memory usage deep equals true again, having changed those data type categories or data types to category, now you can see that not only has the now actually the planet type and detection methods columns take up less memory than the floating data type columns. And that's because some of these values can be saved as like a 1 or 2 bit integer, and each floating value has to be like 8 or 16 bits. Anyway, so we're out of time, so I've got to skip to the key points, but all of this material is available online for you to go over. And then you have exercises. You have exercises as part of the tarball, and for these you will need these 2 data files: COVID-19 _Italy _region and ETA _pop _by _region.txt. So you can construct list or table-like data structures with mixed data types. The main data types are series for 1D objects and data frames for 2D objects. Use primarily select data using the .lock and .ilock with square brackets unless you're grabbing whole columns. Hundreds of attributes, hundreds of methods. If you need to apply more than one, if you need to apply complex or user-defined functions, you have map, add, transform, or apply. Most of the contents of data frames can be grouped by 1 or more columns and can then have aggregate statistical methods called on these grouped objects by group. And most Pandas methods that apply functions can be sped up by multi-threading with numba if they're applied over multiple columns. And you can easily set engine equals numba and engine quarks equals curly braces parallel column tree. And I didn't have time to cover it, but there's also a sparse data type if you have SciPy, if you have data structures that look like SciPy sparse arrays. All right, we're out of time, so we have to reduce. Okay, any questions before we go to a very short break?